Hello everyone.
Hang
So
on.
I'm
Let
okay.
us start. Okay, I think it started. Yeah.
Hello everyone. I'm Prakash. I'm part of the team, the booster dose, and I'll be presenting the paper randomized row swap, mitigating row hammer by breaking spatial correlation between aggressor rows and victim rows. So brief agenda of this presentation. Uh, uh, we'll try to understand the classical row hammer attack, and also we'll see what are the different mitigation techniques available for that attack. And then we'll discuss randomized row swap, that is a new proposal of this paper, and we'll also analyze the result, and finally we'll conclude. Now let's try to understand the classical row hammer. So if we see in the DRAM bank, there will be multiple rows, and each rows is like a word line in conventional memory architecture. Like, so each row you can consider as a word line. So now if a particular row is open, that means activated, and again it is closed. So in that way, if this kind of opening and closing is happening in a particular row, the neighboring rows, that is, say this particular row is R, then R plus 1 and R minus 1, some of the bits of those rows are getting toggled. So that is, like you can see here, right? So now this is called aggressor row, and the neighboring rows, those are called victim rows. So these actually, yeah, this is the conventional or classical row hammer attack. Now, if we see there is a spatial correlation between the aggressor rows and victim rows. Like row 3 is the aggressor row and victim row is row 2 and row 4 in this diagram. And uh, so there is a distance between these they are neighbors, like victim rows are neighbors of the aggressor row. And this was first published in a paper in 2014. So these bits of row 2 and row 4 are getting toggle. So those bits are random in nature, like some values, some of the bit values of row 2 and row 4 are getting toggled, and they can create some issues with the system operation. So let's try to understand the prior victim focus mitigation technique. So mitigation technique is like identify the aggressor row, that is row 3. So first track this particular row, and then the conventional mechanism is to do some refreshing. So refreshing means that is refreshing the row 2 and row 4. So basically you are just instead of doing like conventionally, we have the bank level or all bank level refresh before this detection of this issue. But when this particular row hammer attack was found, so in DDR4 there is a one command was defined, that is called target row refresh. So basically at the granularity of row you can refresh. So with that refresh mechanism, they are refreshing the row 2 and row 4. And this is like a conventional most used mechanism to mitigate the attack. Now, is there any possibility of excessive usage of this kind of refresh can create a new type of row hammer attack? So that we will be looking that we will see in next slide. Yes, that is the possibility. So So a team of researchers from Google, so in the year 2021, they have published one article that is title is half double row hammer attack. So what they're doing, the combination of the aggressor of the previous classical row hammer and the victim, that combination itself creating disturbance in the distance row at 2. So let's try to understand. So this is the middle row 3 is called near aggressor row. Now due to this special refresh, this row 2 and row 4 is also also becoming or also aiding the new type of attack. So if we use say spatial refresh, that is TRR kind of command for several hundreds times, then row 3, row 2 and row 4 in combination they are creating disturbance to the neighboring rows. So here row 1 and row 5. So they term this row 1 and row 5 they are calling as distance 2, because the distance from row 3 it is 2. And this is a new error they found on LPDDR, one of their experiment result they have LPDDR4. So in that observation, what they found that several hundreds of bits of row 1 and row 5 are getting toggled. And this cannot be mitigated with the previous victim focus techniques, mitigation technique. That so this error actually is severe in nature, like it's a very severe kind of error, or many type of attack can be launched with this by exploiting this kind of behavior of the DRAMs. Like all these row 1 and row 5 different bits are getting toggled. Now, before going into the solution, let's get familiarized with the some of the terms which are commonly used in DRAM. So activate command, that is a command which is basically opening that a row. So opening means basically word line voltage you are applying high. So that means that word is accessible and that rows values are getting copied into the corresponding row buffer of that bank. Now TRR, target row refresh. So that is a special kind of refresh which is defined in DDR4, and that is instead of refreshing a complete bank, you can give a row address and it can refresh that particular row, and it will take obviously less amount of time. Now let's try to understand that this activate command, if you are running in a single bank, then there should be a time gap. So in this diagram, actually at clock T0, the one activate command issued by memory controller, and there should be a TRC time gap before issuing the second activate command at TN. Here I have shown as TN. So this is called TRC, the time gap between two successive activate command. Now, okay, let's yeah. So just to get familiarized with DRAM refresh. So this is a capacitor and there's a word line, bit line. As the capacitor will lose the charge if we do after some time, if we do not refresh it. So this refresh time of 64 millisecond means a capacitor can hold the value of a bit till 64 millisecond. If you do not recharge, so that will be lost. So that is called 64 millisecond of refresh window. That is epoch we are saying. Now the number of maximum number of activation that is possible within 64 millisecond. So that is because 64 millisecond and then refresh time, because you can consider that a 16 GB memory will have 16 GB multiplied by 8, 128 bit cells. So if that many capacitor charging will take some time. And if you over 64 millisecond minus that time divided by TRC, so that will give approximately 1.36 millions of activation is possible within a refresh interval or window. And hackers or the attackers intention is uh, to to have some of his own activation within that 1.36 millions. Okay, so row hammer threshold for DDR generation, like we have different DDR generation, DDR3, 4, and LPDDR4, and so to do a row hammer actively at DDR3 level, we needed 139K that many number of activation within a refresh period. Now with the as the technology node is going lower, so the vulnerability is becoming very high. So you can see at low LPDDR4 with only 4.8K, that is 4,800 activation, a attacker can perform a row hammer attack. So that we are denoting T RH equal to 4.8K. So we'll be using this in next subsequent presentation. Okay, now let's try to understand what is the new solution. So they are proposing aggressor focused mitigation. So what they are doing, breaking the spatial correlation between the aggressor row and the victim row. So that means they are trying to reduce the time the aggressor spend with the neighbors. If we within a epoch time, if you can make sure that aggressor does not spend much time with the victims, then probably the row hammer attack may not be possible. So they are just building on that concept. And then periodically they are swapping this aggressor row, say aggressor row, its position to after the threshold number of aggressor row activation. So after some activation, they are swapping with a random row, which is randomly PRNG based generator that is generating the new row address, and they are swapping it. So let's try to understand here. So in a DRAM bank, say we are having this many rows. Now this is aggressor row. Now if some activations are coming on that row and it becomes a aggressor, then what it will do, the swapping will happen. So you can see here row X and aggressor, they are swapped. So here like swap. So then after that, if there is more activation is coming in the new aggressor location, then again it will be swapped. So in that way, this proposal, whatever they propose, that is working. So like after here row Y will come here, then aggressor will go there. So in this way, this will continue. And this location of the new row that is randomly generated using PRNG. Now let's try to understand the uh, how this row swap is happening, and there is a row indirection table. So if you see left side of the figure, so row X and Y are identified, then row X content is copied into a swap buffer, and this swap buffer is inside the memory controller. Now at the second stage, they are copying the content of row Y to the another swap buffer, and that is also in memory controller. Now they are performing, they're writing back X to the location of Y. So then the source and destination, they are in the start step they are doing, and the fourth step they are completely swapped. And this is a tuple list that is containing X and Y and their source and destination. So this is they are keeping in a RIT table. And while doing this operation, because your row size is 8 KB, so that means you have to it needs some time. So approximately in DDR4 they have calculated it is around 2.9 microsecond with a clock frequency of 1.6 gigahertz. Okay, now let's try to understand RRS this proposal in more detail. So suppose a memory access arrived. So that memory access will be forwarded both RIT and HRT. So HRT is a tracking row. So it is basically tracking the aggressor or candidate for swap. And RIT, it is just after swap, it is storing the information that we discussed in the previous slide. And so now if the candidate is present here, then it will go to this location, and it will, this location means that is a new location after swap this location. So this location, the transaction will be or forwarded. Now in case of absent, that means that a particular memory access arrived on a row R, and that is not a candidate for swap. So it will go to the original location of the memory bank. So in this way, the first phase is they are doing. Now in the second phase, this HRT, once it receives the any request, so it analyze, can it be a candidate for swap in the next bus cycle? So it accordingly update the RIT table. So RIT table will have the next candidate for swap. Like in the fourth step, it is, suppose it has detected say row R1 is a candidate. So it will forward to RIT. RIT will remember that in the next cycle, then it will perform this swap operation, that is again with the aggressor row and the new destination row. Now let's try to understand the tracking mechanism. So if you consider in a DRAM, there will be around LPDDR, there will be around 128K of rows. Now we cannot count, we cannot have tracking for each row and counter for each. So then the memory controller size will be like impractical or infeasible kind of. So there are various mechanism to track. This is one of the state of art tracking mechanism. So that is called HRT. So in this, so let's consider this is the initial table. So I'm giving an example with 3 rows. So X, Y, A, X and Z. This is the row address and the corresponding count. Count means that many number of activation is done with that, but with those rows. And there is another field in this table that is called spill counter. So it is initial value is 2. So now let's see, there is another request came with a row address A. Now in that row address, because this row was already present in this table entry, so it incremented to 1, like by 1, that is 7. Now another memory access request came for the row B. Now as row B was not present in the current table, so what the algorithm is, like the spill counter value, they compare with the spill counter value with the count value of each rows, like each table entries, and if it is low, increment by 3. So that means at this stage it is assuming that all other rows except A, X, Z are having the uh, activation count 3. So there are some redundancy here, but this is one of the latest approach. So now if another request come to address C, now what the algorithm says is like you compare that value, any of the count value with the spill counter value. So now it was like X count value of X and spill counter value was equal. So they replace X with C and C count value became 4. So in this way, this tracking mechanism is one of the most efficient mechanism. So they are using, but there are some redundancy, because you might observe that in case of B probably coming for the first time, but it's but all spill counter value 3 means B also having, it is assuming B is also having activation of 3, which may not be true. So the some redundancy is there. So high level, let's try to understand the operation. So aggressor row is identified using the algorithm which is like HRT. Now if the access count in a row is found more than the threshold value, TRRS is a threshold value, then the row swap request is queued. So that is forwarded to the RIT table. Now all future accesses to the swapped rows must be redirected using RIT. So like all the requested will be given like for done through RIT, because it is having all the tuple entries. Now let's try to understand like RIT is sufficiently size to keep swapped row for 64 millisecond. And RIT introduced latency for lookup for DRAM accesses, because you have to do every access, you have to do lookup. So that may incur some latency or add some latency to the direct access path. And a row buffer of a bank is closed after swap, and no accesses are allowed during the swap. So during swap operation, memory is doing, because that time you whatever memory request will be reaching from the memory controller to, I mean from the DRAM is busy. It cannot take any request. So for that swap amount of time, memory will be completely blocked. Now, as we know, this RIT table will have lots of entries, because in a refresh time, there will be many activations, and after threshold interval, you have to swap, and there will be multiple entries. So these entries will to look up to minimize the lookup latency is one of the objective. Otherwise, you may end up with a high latency path. So they are using one collision avoidance table, that is uh, CAT, which is a fully associative cache structure, and this is one of the implementation they used in other other paper. So they have taken from reference from there. So RIT is implemented like a cat structure to store all entries and yet reduce lookup latency like a set associative cache. So it will give a like a full associative cache like, but the latency will be reduced like it will be similar order of set associative cache. So this is the table they are using in their analysis or implementation. Now let's compare this proposed RRS mechanism with victim focused mitigation technique. Those are available as of now. So in this table, if we have they have compared with slowdown. So victim focused mitigation, because it is very low, because it is just issuing one row particular row address and refresh that. So it's a overhead is very DDR traffic will be very low. But in RRS, because we are swapping the row, content is copied every time after the threshold, so that is creating a little bit more performance penalty, like average they are saying 0.4%. Now mitigates classical row hammer, yeah, both of them are doing. Now mitigate complex pattern for far aggressor or half double. So as we have seen in the Google half double case, so that cannot be mitigated by victim focused technique, but RRS can do that. Now another important thing is it works without knowing the DRAM mapping. So DRAM mapping usually processor or manufacturing device manufacturer, they do not disclose in their data sheet or this kind of. So it has to be done a lot of reverse engineering and that way. So it is very challenging, and most of many victim focused mitigation also have a lots of challenge to overcome that. But RRS, because it does not need any identification of random victim and aggressor locations, just or it swaps, so it works for that also. Now let's try to understand another concept, that is block hammer. So this is one of the prior art where they are tracking activation rates using Bloom filter. So Bloom filters, as we know, Bloom filters is very efficient uh, for eliminating false negative, but it detects false positive. So in that, their activation rate they are calculating inside the memory controller. Now they use this tracking to ensure that a row is never activated rapidly to launch an attack. So suppose for 4800 activation required for a row to launch an attack, but this kind of methodology they are not allowing to happen 4800 activation. So that means it's a prevention by design, it is memory controller itself is preventing this kind of attack. And no DRAM ever experience row hammer unsafe. So DRAM row will not get any unsafe activation, like it's by design there, but it has a penalty because there may be some benign application which might need more activations, but this is slowing down because it is having some mechanism to slow down the activation on the highly activated or activated rows. So that benign application also suffer performance penalty, like it will have also have a performance penalty. So they have compared this RRS proposed methodology with block hammer. So here are the observations. So slowdown with block hammer is around 21.7% and average 2%. And slowdown with RRS is around 7.6% and on average 0.4%. So 21.47% is a comparatively uh, big penalty. This is they have published in the this HPCA 2021. Now let's try to understand the performance sensitivity of.
Prakash,
Yes, sir.
I think in the interest of time, we should move on and then conclude quickly because we haven't taken any questions.
Okay. So this is uh, performance sensitivity to row hammer threshold. So basically, they are analyzing the different values of row hammer threshold, and then they so for example, if threshold increases, the slowdown also getting reduces. So this okay. performance overhead of row swap. So here we can see that when they are doing the row swap, and then on average 0.4% slowdown observed over 78 workload. So they are comparing it with baseline. Baseline means without implementing RRS, and after implementing RRS, what is the performance penalty they are comparing here. So it has a huge storage overhead, like 42.9 KB per SRAM per bank, and obviously there are power penalty also. So in summary, it mitigates all type of row hammer attack, slowdown, and SRAM power overhead is also very high, and RIT lookup add extra latency in the data path. So conclusion, this is a mechanism which mitigates like all kind of row hammer attacks, and it also new type of attack like half double, or maybe at distance 3 also in lower technology node can come vulnerability. So those will be mitigated here. So disadvantage approach, it's a on-chip power consumption is very high, performance degradation due to false positive. That is all. That is also problem, and it still have non-zero probability. It's very low, but it's very low probability is there. Okay, now critical points. The author have not discussed impact of false positive on system performance. They have not done analysis or have not shown anything like that, and the paper does not report any analysis of variation of false positive rate and with change to HRT size. So HRT size also, and they are not have not done any kind of analysis or have not shown here. A point to discuss possibility of side channel attack during swap and increase the speculation based attack due to blocking of accesses. So it may happen just so in speculative attack you are in a worst case your last instruction is a load to the, and when the load appear to the memory controller, the swap has already started. So it has to be halted for 2.9 microsecond, and that might give some opportunity to speculative attack. So these are the different points, and possible extension of this work, like maybe we can it better heuristic algorithm to swap the candidate instead of pure random, and reduction in false positive, because there will be some benign application, and those are unnecessarily getting tracked. So if some sort of segregation can be done, so it may be a possible work. So these are the references. Thank you. Questions? Yeah, so I am open for any question.
Yeah, we can take maximum 1 or 2 questions.
Hi Prakash.
Yes.
My question is that in the current slide, what is this possible side channel attack during swap? What do you mean by this?
So like when swap will happen, so suppose some attacker process is there, and there will be some other process, say process 1 and process 2. So now process 1, suppose it is in swap. So when the process 1 or 2 can estimate the access time. Suppose process 1 has made a access and that time swap started. So it may understand, okay, something happening because I am blocked for 2.9 microsecond. And in other transaction, though that time swap was not happening. So then he might that process might understand, okay, now my transaction is passing through because something not happening there. So this kind of because there will be difference in access time, so that maybe they can some attacker can play with that.
Basically, it's a covert channel, right? Not a side channel. The scenario that you explained.
Right. So yeah, so that.
But what is it revealing? So it's just revealing that whether the swap has started or not, like the swap is
Right.
going or not, right?
Right.
Okay.
But yeah, so that actually maybe we need to think like what can be extracted by this by observing this event in a continuous period of time, like continuous time. If this is observed, then something the row swapping or some. I am not like something can be observed with this timing.
Okay, I'm only able to think of that let's say if there is a row hammer attacker and so it was able to send the accesses to DRAM, and after a certain time it will its process will be halted, right? The process will be on hold, kind of. The request will not be served, which were going to the DRAM. So only thing that attacker will get to know is that okay, so its accesses has reached to a certain limit, and now the rows are getting swapped. That is the only thing that I'm able to think of. But okay, yeah, I got your point. Thank you.
Well,
Okay, let's move on to the next presentation.
Yeah, I'm the next presenter. Okay, I'll just share my screen. Hope my screen is visible.
Yeah, you can switch on your camera also if you have good bandwidth internet. Otherwise, it's fine. Yeah, perfect.
Yeah. All right. So I'm Smith Gangude. In behalf of Team 8, I'll be presenting DAC guys, mitigating memory timing side channel attacks. So the problem is that existence of shared memory gives way to timing side channel attacks, which we have seen in cache as well. The only difference being here is that it is also possible in DRAM, and the channel being the memory controller. So the attacker can cause contention on the shared memory in memory controller with its own request to gain secret information, which could be encoded in victim's access pattern and basically leak that secret information. So visually, we can see that so the victim has some access pattern which could be dependent on its own secret information, say bits 0 or 1. It accesses those memory requests. It issues those requests on the memory controller, and the attacker then causes contention on the shared memory. And since the information is already encoded in the pattern itself, the attacker can then guess whether the what the secret information was. So we'll see the three properties of existing solutions, which is the security, whether the existing solutions for this attack taken into consideration all the timing resolutions, whether they are performant enough or they cause degradation of the entire system, or and whether they need prior information of the co-running processes. So the first is camouflage, which takes on the approach of traffic shaping. Basically, we take in the victim's memory access pattern and shape it into an access pattern which is indistinguishable to the attacker. So in terms of security, it does not work for finely grained timing attacks. However, it is performant enough, and but it does require prior information of the processes which will be simultaneously running with the process we want to protect. So, which is a undesired property. Second, we have the fixed service, which takes on the approach of temporal partitioning, basically having fixed slots for issuing memory requests, fixed timing slots. It does provide security on all timing resolution. However, since we have fixed on some fixed intervals, the timing slots are there, so it's not really that performant enough. But it also doesn't require any information of simultaneous processes which will be done simultaneously with the process we want to protect. So Q in that, guys. The very high level goal of this paper is to mitigate memory side channel attacks by hiding the victim's access pattern. While doing so, we also want to maintain the security on all timing resolutions and also not cause significant performance degradation. So why is it a big deal? So since we've seen that existing solutions, there are either security loopholes in terms of timing resolution in the case of camouflage, or there is a drop in performance in case of fixed service. So DAC guys actually achieves a 12% speed up to the state of the art, which is the fixed service solution. And also it is versatile enough to for unknown delays caused by simultaneously running processes, and it also works for fine-grained timing attacks. So on a very high level, the approach is very simple. We want to take the victim's memory access pattern, which could encode secret information, and put it into a request shaper, and then and using some predefined sets of and using some predefined set of hints, we want to shape the memory access pattern of the victim to an indistinguishable pattern so that the attacker cannot guess what the secret information is. So here we require two things. We require some representation of memory access patterns so that we can input the victim's pattern and also output an indistinguishable pattern. And we also need a predefined set of patterns which are safe, which could be used as hints for the request shaper.
So, yeah, I have a question here before you move on.
Sure.
So how do you identify or distinguish a victim process from other processes?
We actually do offline profiling. So we already said that this is the victim process, and we want to do an offline profiling of its memory access, and then we start the process.
Oh, okay.
So this is done before the victim actually starts processing.
Okay, got it.
Yeah, so since we required how the patterns could be represented, so QN directed a cyclic request graph, or RDAC for short. This paper introduces this representation of memory access patterns, which will be used throughout the solution. So and also the templates will be a set of these RDACs, predefined RDACs, which will create depending on the victim's input access pattern, which will create a search space. And depending on that search space, we'll come up with a final RDAC for the victim. We'll come up with a final RDAC for the victim depending on how it performs in the profiling stage, where we check for its average bandwidth allocation and how it performs, what is its performance in terms of IPC. And then this final RDAC will be used in the request shaper. Additionally, we'll be using a closed row policy for the DRAM banks. So since DAC guys can hide the victim's access pattern, but it can't really do anything about getting hits in the same row, which the attacker can take advantage of. So closed row policy basically means that temporarily adjacent memory requests on the same row will not occur in a hit. So this is a complement to the solution. So we'll look at how these RDAGs actually look like. So this is just a directed acyclic graph where the vertex represents a memory requests. The edge represents the dependency between two memory requests. So let's say that there is an edge between U1 and U3 memory requests. So U3 can only be started after the completion of U1. So by putting an edge between these two requests, we represent that. And so similarly, since any two requests don't have an edge between them, that implies that they are independent requests and which could be executed parallelly. The weights on the edges represent the inter-request delay, which could be the queuing delay or some computational delay in the program. And these RDAGs will be used as a representation of victim's memory access pattern, and as well as the templates will use these, and the request shaper's output will also be in the form of RDAGs. So profiling As I've said, that we do an offline profiling of the victim's process, which is done in isolation from the other simultaneously running processes. So attack guys does not require any prior information about other processes, what their access pattern is. So the entire goal is to convert the original RDAC or the victim's pattern to a defense RDAC, which is the pattern which does not encode any secret information. And this defense RDAC is then used by the request shaper. So just as an example, let's say that the original RDAC for a victim, for in the case of secret 0, has memory requests in the interval of 100 time units, and in case of secret 1 has memory requests in the interval of 200 time units. So feeding these two RDACs to the request shaper will come up with an defense RDAC, which has 150, which has memory requests per 150 time units. So how does this actually protect the memory, protect from the attacker? So in case of, we'll take these two cases again. In case of secret 0, we had the original pattern, which was in the interval of 100 time units, and the shaper's output was in the interval of 150 time units. So initially, the shaper's output and the original victim's access matches. So we emit the victim's request itself. Next, after 100 cycles, the victim again emits a request. However, the shaper hasn't emitted any request. So we queue this request, and then after 50 time units, after the shaper actually outputs its own request, then we'll see whether the queue contains any victim request. If it does contain it, then we'll emit that request. So this was in case of secret 0, where one thing to notice is that the frequency of requests of the shaper with respect to the original request was slower. So in case of secret 1, this will be inverse. So the original requests are actually coming slower, but the shaper's requests are coming faster. So initially, again, the first request matches the shaper's output. So we will just emit the victim's original request. However, after 150 time units, the shaper will output another request. But seeing that no other victim's request is actually pending or queued, we'll throw in a fake request. So this fake request could be on a random row. And then again, we'll continue the same process. So for secret 0 as well as secret 1, we'll have the same memory access pattern. So it doesn't encode any secret information as of now. So this solution is also applicable for multi-threaded programs. However, we do have trade-offs. So we can provide a single defense RDAC to all threads, which will reduce the online. So which will actually increase the offline profiling trade-off. So we will have to profile all the threads, and then according to the all threads, we provide a single defense RDAC. However, it performs well in terms of online when the program actually runs. So we will have lesser number of fake requests. In the other case, where each thread can get a different defense RDAC, we'll actually save some overhead in the offline profiling trade-off. So we don't have to consider all the threads together. We can actually profile each thread individually. But during the online performance, it does increase the number of fake requests. So each thread will have a different shaper output, which could increase the number of fake requests. So evaluating it, we'll evaluate with respect to fixed service or an adaptation of fixed service, which is the bank triple alternation, which is adapted to make it more performant. The setup here is that it is running on a two-core system, and we have one protected program, which is the doctist program, and one spec benchmark. So the dark gray one is the DAG guys, and the light gray is the FSBTA. In almost all cases, you can see that the DAG guys performs better than the FSBTA. In general as well, for a two-core system, it performs 6%. It gains a 6% speed up with respect to FSBTA. However, in some cases, we can see that FSBT actually performs better. So if these benchmarks, such as the Leela benchmark, actually the benchmark, the co-running processes do not require that, do not account for that much bandwidth allocation. So they don't issue much memory requests. However, the template RDAGs we have given as hints to the request shaper, they try to accommodate co-running processes bandwidth. So for such cases, we'll require some complex templates, which is not currently in the DAG solution. In the second experiment, we'll see how it scales with more number of processes, protected as well as unprotected, and with more number of cores. Again, we see that in general it performs. So we have 4 protected programs this time, 2 docdist programs and 2 DNA pattern sequencing programs, and 4 identical copies of one spec benchmark. So in general, we see that again DAG guys performs better than the FSBTA program, and on average it performs it gains a 12% speed up with respect to the fixed service. However, there is a 34% system slowdown. So, in conclusion, this paper presents a novel way of representing memory access patterns, which is the RDACs, which are general and which can be used to shape victims' access pattern to something which is indistinguishable, which does not encode any secret information, which are also general enough to accommodate all the timing resolution, and versatile enough to accommodate simultaneously running processes bandwidths. And we gain as we've seen, we gain a 12% speed up in case of the state-of-the-art fixed service. Thank you. And all the graphs and images are taken, have adapted or taken from the DAG guys paper. Before discussing, if there are any questions.
Yeah, I have a few questions. My first question is the FSBTS, I think something you mentioned, right? Fixed service. So this is the temporal one, right? That you mentioned in the beginning.
Yes.
This is same, which is secure but has performance overhead.
Yes.
Okay, and can you quickly give me the reason? What is the security issue in camouflage?
Okay, so it isn't really discussed in details, but however, they say that it doesn't work for finely grained timing resolution attacks.
Okay, yeah, fine. Okay, I'll take that. So my next question is that you mentioned about the weights. So at somewhere in your slides you were yeah. So this 200, yeah, these weights are the same which you mentioned like after few slides, right? Though 200, 150, that number is the weight here.
Yes.
Is it?
Yeah, these are the weights.
Okay, so here in RDAG, they are just finding out the acyclic graphs and then assigning some weights, right?
So these weights actually represent how much delay will be in between these two.
Yeah, yes.
Yeah.
Okay, so my question is that what if I just identify the this acyclic graphs and then I process the request randomly instead of changing the I mean instead of assigning the time. So that also will help in security, right?
I'm sorry, I don't get what you're saying.
Yeah, I'm saying that as per my understanding, because they are now they are changing the cycles which are consumed between different requests. So that is how the attacker will not get the intuition that how many exact cycles were taken before his or her request was processed, right? So I'm just saying that you find out the acyclic graph because you mentioned that there are some requests which has some dependency between each other, right?
Yeah.
So that is why you need to find out that dependency. So once you have found out the acyclic graph, after that you just randomize the request.
Randomize the request.
Yes. Instead of changing, I mean, you just randomize the order, kind of. So will that make any difference?
It would make sense in terms of the request which does not have any dependency such as U2 and U3, but let's say U1, U2, U2 and U4. These are dependent on each other. So I think in that case, we can't really randomize these.
Okay. Yeah, thanks.
So if there are no questions, the 2 points to discuss is that use of RDAG-like structures for other security strategies. So maybe in terms of multi-threaded cores or other security domains. And another point to discuss is that instead of issuing fake requests, we can use that opportunity to do useful tasks such as prefetching or any other task we want to hide latency of.
Okay. So Devasis, you can stop the recording. Hari, are you there?